Welcome back to Applied Mathematics. In this video, I want to look at exact trigonometric values. When I say exact values, I'm generally talking about things where your calculator is going to be less than helpful in trying to get things across. A lot of what we're going to be talking about here is going to involve some calculations where your calculator could do the work and give you a decimal approximation. But again, we are looking for the exact trigonometric value, so that's going to make a bit of a difference. The first thing I want to look at are what are called the special angles. Let me get my head out of the way and I'll list out what I mean. Let's use a skinnier pen. All right. So there are a couple of angles that are called the special angles, and I'm going to give you the special angles in both degrees and in radians. 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. It's every 15 degrees, really. Why are 15 and 75 skipped? Because the representation is really ugly. It turns out that if we look at these 5 angles, 0, 30, 45, 60, and 90, it is really easy to memorize the values of some of the trigonometric functions. In radians, you can go and do the conversion. This is 0, pi over 6, pi over 4, pi over 3, and pi over 2. And the reason that these are called the special angles is because calculating or remembering the sign, once you remember where the series is very simple. I'm going to take the numbers starting at 0 and counting up to 4. I'm going to take the square root of each of those numbers, and I'm going to divide by 2. Square root of 0 is 0. 0 divided by 2 is still 0. Square root of 1 is 1. 1 divided by 2 is just 1/2. Can't really do anything with square root of 2 or square root of 3, so they stay alone. Square root of 4 is 2, and 2 divided by 2 is 1. So we get this list: 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. And these are the sign of the special angles. And that pattern is why we talk about it, why it's useful. You may also talk in geometry in some other contexts about the 45-45-90 triangle or the 30-60-90 triangle. They're fairly easy to work with geometrically, and so there's another reason that these particular angles tend to show up. But the other thing we can do with the special angles is take advantage of what's known as the cofunction identity. I'm going to fill out the table here, and then I'll talk about why it works. To find the cosine of these angles, we just take the values that are on the table and write them in the opposite order. That's it. Once you memorize the list for sine, it's the same list going backwards, and you have cosine. And the reason for that is if we think about a triangle, we know that the third angle up here, if we've got a right angle, we've got an angle called theta. Well, 180 minus 90 is 90, and then 90 degrees minus theta is the angle up here. And so looking at our triangle, when theta is 30 degrees, that means that the angle over here is 60 degrees. And so sine of 30 degrees is 1/2. Opposite side has length 1, hypotenuse has length 2, right? Opposite over hypotenuse is sine. Well, using the Pythagorean theorem, that third side is square root of 3, right? 1 squared plus square root of 3 squared is equal to 2 squared. You can plug that in and check to see that it works. Using the Pythagorean theorem, we know that 1, 2, and square root of 3 are the lengths of the sides of a 30, 60, 90 triangle. So for sine of 30 degrees, you want to take the opposite side over the hypotenuse. For cosine of 30 degrees, you want to take the adjacent side over the hypotenuse. But then if we look at 60 degrees, it's the same triangle, we've just changed the names. This is the side that's opposite 60 degrees. So if I want to take the sine of 60, I get square root of 3 over 2. And if I want to take the cosine of 60, the adjacent side is 1 and the hypotenuse is 2. So that's why the same two measurements show up for 30 degrees and 60 degrees, just swapping which one is sine and which one is cosine. We call that the cofunction identity. The sine of an angle is the same thing as the cosine of the complementary angle. That's literally what cosine means. It's the complementary angle's sine, just shorthanded. Depending, as I've said many times, depending on where you're continuing onward from here, if you continue to study with me, I'm going to encourage that you have this list somewhere that you can readily reference. Being able to regurgitate it by writing it down is great. Having it written down on a reference sheet or something else that is at hand as you're working through problems involving trigonometry is great. If you're going to go on and eventually take a math class with someone else, a lot of mathematics instructors still think that having this list memorized is valuable. So that might be something that you have coming up in your future. I don't have a crystal ball to know for certain. Right. That's one thing we can do with exact values. It's not the only thing we can do. In fact, I think that this is a little bit more fun. Given that sine of theta is equal to 3/5, what are cosine of theta and tangent of theta? Well, you can in fact use a calculator to answer this question, but I want to look for exact values instead. And so in order to do that, I'm going to start by drawing the right triangle. Marking down where my angle theta is and where my right angle is. And I know that sine is opposite over hypotenuse. So the ratio here, opposite over hypotenuse, is 3/5. I can write that into my triangle by just marking down that the opposite side is 3 and the hypotenuse is 5. Now I've got a right triangle with two sides known. And I can put that information into the Pythagorean theorem, or in this particular case, we have a special triangle that you might know offhand. If not, the calculation isn't too bad. We can get that the third side of this triangle is 4. Now that I have the third side of the triangle, I have all the information I need to figure out cosine of theta and tangent of theta. Cosine is adjacent over hypotenuse. 4 is the adjacent leg, and 5 is the hypotenuse. So cosine of theta is 4/5. And then the tangent of theta, well, tangent is opposite over adjacent. The opposite side is 3. The adjacent side is 4. The tangent of this angle is 3/4. Sometimes when we do this sort of thing, the numbers don't work out nearly so nicely. For example, if I know that the tangent of theta is 2/3, and I need to figure out the secant of theta, I can approach this problem the same way. I can draw out my triangle. I can mark in my angle theta. I can remember that tangent is opposite over adjacent. The opposite side of this triangle is over here. The adjacent side is here. So opposite over adjacent, 2/3. The easiest triangle that gives me that has an opposite side length 2 and an adjacent side length 3. And again, using the Pythagorean theorem, I get that the third side of this triangle has a length square root of 13. And so knowing that, I can now think about secant. All right, secant of theta, that was the ratio hypotenuse over adjacent. The hypotenuse of this triangle is root 13. The adjacent side is 3. So secant of theta is square root of 13 divided by 3. All right, that's all I have for you with this video. Take some time to work through some practice problems, see where you can get to with this, and I'll see you next time.